So for this video, we'll be looking at how to factor trinomials of the form x squared plus bx plus c. Here we are assuming that our leading coefficient is a positive 1, even if it's not written there. And what we're going to be looking for as we try to do this factoring method is we're going to look for pairs of integers that have a product of c, which is going to be our constant term in the polynomial, and they have a sum of b, which is going to be the coefficient of our middle term or our x term. And so just as a review before we go into the process, again, if we think about the reverse of this process, taking two binomials that are already factored, distributing them to create a simplified polynomial. If we had something like x plus 2 times x plus 4, for example. In this format, this is a polynomial that has been factored into two binomials, which is going to be our goal in this process. And so if we didn't want them to stay factored, we would distribute here, so do the FOIL method, if you will, to get a polynomial that results from doing this, the simplified version. So the x times the x would give me x to the second power. My x times my 4 would give me 4x. My 2 times my x would give me 2x. And my 2 times my 4 would give me 8. And so when I cleaned this up and combined my like terms, I would get the trinomial x squared plus 6x plus 8. These two polynomials are the same thing. This is the simplified or multiplied out version of the polynomial, and this is the factored form of that polynomial. And so the reason I do this is to make sure that we're seeing what happened when we combine these things and we ended up getting what we're going to be starting with, which is this three-term polynomial, so that it can help us move backwards into the factored form of the polynomial. So we've got this constant term of 8, and this 8 came from us multiplying this positive 2 and this positive 4 together, which is why up here we said I want a pair of integers with a product of c, which is my constant term in the polynomial. And then we said, when to get this middle term, 6x, we had to take this 2x, which got its coefficient from the 2, and this 4x, which gets its coefficient from this 4, so 4x and 2x, and we added them together to create this 6x in the polynomial, which is why we say here that we want those integers to also have a further condition, not only of this product of c, but also combining with a sum to make that middle coefficient of b, because that's just how this two factors will interact with each other every time we FOIL them out or distribute them out to create the three-term polynomial. So when we work backwards, we're going to focus on looking for integers that make this kind of match of a particular product and a particular sum. And I often tell my students to make a table when we do this, not so much because these are so complicated, but because when we change the coefficient to not be a leading term of 1, we're going to use essentially the same method, but we'll have more to keep track of there. So if we had the polynomial x squared plus 12x plus 27, if we're thinking about how these numbers combined, I know I'm going to want it to factor into x plus or minus something times another x plus or minus something, because that's our goal in factoring these trinomials into a pair of binomials. So our goal is to finish these off by figuring out what are the proper integers that combine with a product to one value and a sum to another value. So I want a product of 9, and I want a product of 27 and a sum of 12. So when I think about what I need to multiply to get 27, 9 and 3, both positive to give me a positive product, do multiply to 27, and when I add 9 and 3, they do add up to 12, which means this is the only pair of numbers that can complete these factors properly to result in this polynomial when I recombine them. So here I would say x plus 9 and x plus 3. So this is the factored form of this trinomial that they want me to be able to factor. And again, if we don't trust that we've factored completely correctly, we can always check ourselves by recombining them through distribution and making sure that that distribution results in the same polynomial we began with. So here, if we decided to check, x times x would give us that x squared, x times 3 would give us 3x, 9 times x would give us 9x, and 9 times 3 would give us 27. And if we simplified that by combining our like terms, we would get x squared plus 12x plus 27, which is the polynomial that we began with. So that reconfirms that these two polynomials, one that is in its multiplied out form or simplified form, and one that is in its factored form, are equal to each other. So this would be our end factorization. Again, not a required step, just a step I want to remind us we can always follow when we're factoring. For this next polynomial, x squared minus 2x minus 24, I want a product not only of 24, but of negative 24. And I want a sum not of positive 2, but of negative 2, because that's what the polynomial tells me. So to multiply 24, let's say I started with something like 2 and 12. If I want the product to be negative, I know one of these values has to be negative. If I want the sum to also be negative, then I need the larger of the two values to be negative in order for me to add them together and get a negative sum. So that means here I would need 2 and negative 12. But when I add up 2 and negative 12, it gives me negative 10, which is not negative 2. So I know that this is not the pair for me to use in my factoring. So I need to go find another one. I need two numbers that are closer together. So let's say we tried 6 and 4. Again, I need them to be mixed signs to get that negative quantity. I still need the larger one to be negative so that I get this negative sum. So I need negative 6 and positive 4. Negative 6 times positive 4 does multiply to negative 24. And when I add them together, negative 6 plus 4 does equal negative 2. So it meets both of these conditions, which means these are the only two numbers I need for my factorization. So x squared minus 2x minus 24, it factors into x minus 6 times x plus 4. And then we get to be done with that particular problem. For this one here, we're trying to factor x squared minus 5x plus 6. I'm looking for two numbers that multiply to a positive 6 and that add up to a negative 5. So to get 6, I could do 6 and 1. To get a positive product but a negative sum, that means that both of my factored values have to be negative. Negative 6 and negative 1 do multiply to negative 6. But if I add them, negative 6 and negative 1 add up to negative 7, which is not negative 5. So that means this pairing is not going to work. Two other numbers that multiply to negative 6 would be negative 2, positive 6 would be negative 2 and negative 3. Negative 2 and negative 3 multiply to positive 6. And when I add negative 2 and negative 3, I get negative 5, which means this is the only pairing I need. So this is going to factor into x minus 3 and x minus 2. If you rearrange the factors and wrote, say, x minus 2 times x minus 3 instead, they're both correct, whichever order we decide to choose to write them in. These are both proper factorizations of this original polynomial. Here on this example, the constant term is negative 12, so I want two numbers that multiply to negative 12. The coefficient in front of my middle term is an understood positive 1, so I want my two numbers to add up to positive 1. To get a negative product, again, I need a mixed sign, so one positive, one negative. To get a positive middle term, or a positive addition, that means the larger of the two values has to be positive. So for 12, I could do something like 6 and 2. and here it would have to be 6 and negative 2. But 6 and negative 2 add up to positive 4, which is not positive 1. So that pairing is not going to work for us. 3 and 4 also multiply to negative 12. If I made that negative 3 and positive 4, when I add them together, I do get that positive 1. So that must be the two values I need for my factors. So this is going to factor into x minus 3 times x plus 4. Again, if you change the order and wrote it as x plus 4 times x minus 3, you would still be correct in your factorization. For the last example I wanted to go over, this is a little different. When we look at this polynomial, negative 2x to the second power plus 4x plus 16, this does not have that implied leading coefficient of a positive 1, so that's a problem for us. But when we look at these numbers, 2, 4, 16, these all have a greatest common factor of 2. Because this 2 happens to be negative, we'll also take the negative as a greatest common factor. So on a problem like this, that doesn't meet the standard form they're asking me to have it meet, that means they're wanting me to look for a greatest common factor before I start following this other method. So here, I'm going to do my GCF of negative 2 first, just like in a previous example we did, or GCF methods we did. Negative 2x squared divided by negative 2 makes this just plain old x squared. 4x divided by negative 2 makes this negative 2x. And 16 divided by negative 2 makes this negative 8. So now I'm going to keep bringing this negative 2 with me because it's a factor that I'm not allowed to drop. And I'm going to focus on the method we were doing before with this polynomial right here. So this polynomial is telling me that I want two numbers that multiply to negative 8, and I want them to add to negative 2. To get this negative product, I need a positive and a negative value to be combined. To make their sum negative as well, that's telling me the larger of the two values has to be negative. So that means here I could use negative 4 and positive 2. They do multiply to negative 8. When I add them together, it does equal negative 2. So this is the pairing that's going to work for us to factor this polynomial in here. So when I go to the last step of factoring, again, this negative 2 doesn't go away. We never drop our factors, so it's going to keep coming along with us. We're going to have x minus 4 and x plus 2. And so this here, these three factors, will be the final factorization of the original polynomial they gave us. I hope that helps. Please let me know if you have any questions.